In section 4.3, we are going to start talking about right triangle trigonometry. So where you've heard about right triangle trigonometry before is in SOHCAHTOA, right? And remember that SOHCAHTOA is just an acronym for the sine of a function is opposite over hypotenuse, the cosine is adjacent over hypotenuse, and the tangent is opposite over adjacent. But then we also have three other functions that we have to talk about, which are your cosecant, your secant, and your cotangent. So the acronym that I use for that is CHO. So that's your cosecant is hypotenuse over opposite, secant is hypotenuse over adjacent, and cotangent is adjacent over opposite. So if this is SOHCAHTOA, and we've always kind of talked about SOHCAHTOA like it's a person, then CHO we could just assume is her cousin, right? All right, so what we're going to learn is we're going to talk about trig functions of acute angles and use calculators just to help us in those evaluations. We'll use fundamental trig identities. So we're going to get into some identities today, and there is a formula sheet. So if you check out your Chapter 4 formula sheet in Google Classroom, you'll see that there's way more formulas than you need right now, but a lot that we will end up using in the next few chapters, so we put them all together. And then we'll use trig functions to model and solve real-life problems. Okay, so our 6 trig functions, we kind of talked about a few seconds ago with the SOHCAHTOA and the CHO, right? But they're all based on the right triangle and on an angle measure. So if you have an angle and your theta, remember then your side opposite is across, your side adjacent is the adjacent leg, and then the hypotenuse is always across from the right angle. So if we look, these are your 6 trig functions. These are the ones you need to know. And it's all of the ratios. So the sine has the ratio of the opposite side over hypotenuse. The cosecant, if you notice, these two are related because your cosecant is just the reciprocal of the sine. So if you know the ratio for sine, you can use its reciprocal to find the ratio for cosecant. Cosine is adjacent over hypotenuse, which means that secant is its reciprocal, so hypotenuse over adjacent, and tangent is opposite over adjacent, so cotangent is adjacent over opposite. So if we look at this first example, it says use the triangle to find the exact values of the 6 trig ratios. So they give us this triangle and they tell us that the 2 legs are 3 and 4. It's a right triangle, so we could use Pythagorean theorem to find the hypotenuse. So we could say 3 squared plus 4 squared equals c squared. So 9 plus 16 equals c squared. So 25 is c squared, which means that c is 5. Okay, or maybe you just recognized from the beginning that it was a 3, 4, 5 triangle, and you could go right to that. So starting with our ratios, let's start with our sine. So the ratio of our sine, and if this is our theta over here, our opposite side is 4 and our hypotenuse is 5. So we say sine is 4/5, which means the cosecant is the reciprocal. So the cosecant is 5/4. Cosine is the adjacent side, which is 3 over the hypotenuse. So 3/5, which means that the secant is the reciprocal, which is 5/3. And the tangent of theta is opposite over adjacent, so 4/3, which makes the cotangent of theta the reciprocal of theta, so we would have 3/4. And then here's your exact values. These are from the unit circle that we talked about mostly in section 4.2. The value for 30 degrees is the same as pi over 6, and the sine of those is 1/2, which means the cosine is root 3 over 2, and the tangent is root 3 over 3. So the sine and the cosine, I feel like most of you will have these memorized pretty soon here. The tangent, something that you need to think about is memorizing tangent rather than trying to solve those algebraically. So I use a little trick where when we're looking at the tangent of pi over 6, I know that you could get 6 by adding 3 plus 3. So the root 3 over 3 goes with when the tangent is pi over 6. Okay? So when the tangent is just pi over 3, it is just the root 3. And then the tangent of pi over 4 is 1, because remember, tangent is sine over cosine, and so if we do root 2 over 2, and we divide it by root 2 over 2, we would get 1. All right, so we have the complementary angle type theorems with the idea that because, I guess going back to this slide here, I kind of skipped over it at the bottom, because sine of 30 is 1/2 and cosine of 60 is 1/2, right? Because 30 and 60 are complementary angles. So whenever you have these complementary angles, you have some of these rules here, where if you do the sine of 90 minus an angle measure, it would be the same thing as the cosine of that angle measure. Okay, you have the tangent, the secant, the cosine, the cotangent, and the cosecant. So there's all of these rules. Again, these are on your formula sheet, and you can find your formula sheet in Google Classroom under Chapter 4. It's the Chapter 4 formula sheet. If you're in person, I will have a copy for you to hand out to you. But again, if you're not in person, you're going to have to look at your formula sheet from Google Classroom. All right, so then we also have all of these trig identities, so these relationships that are equal to each other. So we could say, in this case, that the sine is the same thing as 1 over cosecant, the cosine is 1 over secant, the tangent is 1 over cotangent, and then the same is true. Cosecant is 1 over sine, secant is 1 over cosine, and cotangent is 1 over tangent. Or if tangent is sine over cosine, cotangent is cosine over sine. So those are all your reciprocal identities. Then we have our Pythagorean identities. The big one, sine squared plus cosine squared equals 1. But we also have that 1 plus tangent squared equals secant squared, and 1 plus cotangent squared equals cosecant squared. Okay, and again, you will find these on that formula sheet. So you do not need to have these memorized, but you need to know where they are on the formula sheet and how to use them. So let's do a few examples with these identities. It says theta is an acute angle such that the cosine of theta is 0.8. Find the values of sine and tangent using trigonometric identities. So here, if they give us a cosine, and for part A they want us to find the sine, we could use, so for part A, we could use that sine squared of theta plus cosine squared of theta equals 1. We could use our Pythagorean identity. Since we know the value for cosine, and we could rewrite this as the sine of theta squared plus the cosine of theta squared equals 1. So sometimes visually that makes more sense when we're doing some substitutions. Since the cosine is 0.8, in for this whole cosine, I can substitute a 0.8. So I'm going to have the sine of theta squared plus 0.8 squared equals 1. So if I have the sine of theta squared, if I subtract 0.8 squared, and 0.8 squared is just 0.64, I get 0.36. So then to solve for sine of theta, I can take the square root of both sides, and I get that the sine of theta equals 0.6. And that would be your answer for A. For B, if we want to find the tangent of theta, And the information we have is cosine is 0.8, but we just solved that sine was 0.6. Remember that the tangent of theta is the sine over the cosine. So we can use those values. Since the sine is 0.6, we could say that we have 0.6 over 0.8, right? And 0.6 divided by 0.8 gives us 0.75, right? So the tangent of theta in this case would be 0.75. All right, we have another one here, another tangent. They give us a tangent value as 1/3. And for A, we want to find cotangent. So this one's pretty quick if you remember the reciprocals. Remember that cotangent of theta is the same thing as 1 over the tangent of theta. They're just reciprocals, right? Oh, I wrote cosine. Sorry, right here. That needed to be a cotangent. So cotangent is 1 over tangent. So we could say that the cotangent of theta is 1 over 1/3, right? And 1 over 1/3 would just be 3. The second part, though, when we have that the secant of theta, right? We want to find secant of theta, and we're given information about tangent. So let's go back a couple slides and look at our trig identities. And if you notice, this one right here, it says 1 plus tangent squared equals secant squared. And we have information about tangent that we could substitute in. So let's use 1 plus tangent squared equals secant squared. And again, if it makes more sense, rewrite this as the tangent of theta squared equals the secant of theta squared. Since we know tangent is 1/3, we can say 1 plus 1/3 squared equals the secant squared. 1/3 squared is 1/9, so we have 1 plus 1/9 equals the secant of theta squared. And then 1 plus 1/9, we need common denominators. So this 1 you could change into 9 over 9. So if you have 9 over 9 plus 1 over 9, we have 10/9 equals the secant of theta squared, which means we need to take the square root of both sides. And if we were to simplify that, that's the same thing as the square root of 10 over the square root of 9. The square root of 10 doesn't simplify, so we would leave that as the square root of 10, but the square root of 9 is 3. So we could say that the root 10 over 3 is our value for the secant of theta. And then on example 7, we're using trig identities to transform one side into the other. So in order to do that, in this case, this right side is already 1. So we need to rewrite maybe the cosine or the secant in a way that will get this left side to simplify to be 1. So for this one, I'm going to leave the cosine as cosine. But remember, with your reciprocal identities, the secant is 1 over cosine. Right, so we could rewrite the left side as cosine times 1 over cosine, which gives you cosine over cosine. And cosine over cosine is 1, right? And we needed it to be the same as 1, right? So we got those two sides to be the same, and we're excited about it. So we say, yep. All right, so this next one is a little bit tricky. I would probably first start by foiling it, because if you notice these two factors, we have secant plus tangent, and we have a secant minus tangent. So usually when you have the same things in your factors and one's plus and one's minus, that middle term will end up canceling out. So if we FOIL this out, we have secant and secant, so that's secant squared. Secant and negative tangent, so that's negative secant times tangent. And then we have tangent times secant, so then we have a positive secant times tangent. And then we have tangent and negative tangent, so we have a negative tangent squared theta. And again, we want that to somehow simplify down to be 1. So if we look to start simplifying, right, this negative secant tangent and positive secant tangent, so we're left with a secant squared minus a tangent squared. Okay, and secant squared minus tangent squared, again, let's go back a couple slides to look at our identities, which we should have, right? But we don't have any secant squared minus tangent squared, but we do have that secant squared is 1 plus tangent squared. So what I'm going to do is, in for my secant squared, I'm going to substitute a 1 plus tangent squared. So in for this, I'm going to change that to 1 plus tangent squared because that was one of my identities. And then I'm going to subtract tangent squared. Okay, so this part right here was just substituted in for that from your identities. Your positive tangent and your negative tangent are 0, and you're left with 1. And remember, if we go back to the beginning, we wanted our left side to be 1, so we can be excited about that and say, yep. All right, and then we have our applications. So remember, applications really just means story problems. And so a couple pieces of vocabulary that you need to remember are the difference between your angle of elevation and your angle of depression. So these are both based on a horizontal. So if you're the observer and you're looking up, that's your angle of elevation. However, if you're the observer and you're looking down, the angle from that horizontal is your angle of depression. Okay, so if you need to refer back to that slide if you get confused about those. But let's look at this one story problem. And then in our next section that we're going to work on is actually all story problems. So this is just kind of a warm up to that. So this says a surveyor is standing 50 feet from the base of the tree. Right, so that's this distance right here that they gave us. This is their 50 feet from the base of the tree. If I draw this a little bit bigger, so this is our tree, and our surveyor is here, and that distance is 50. And it says the surveyor measures the angle of elevation to the top of the tree is 71.5. So if this is the top of my tree, and the guy's looking up, or the girl, either one, this is 71.5 degrees. And then the question is, how tall is the tree? Right, so this is our tree over here. We'll call that side T. We want to know how tall the tree is. So we have to think about, again, we're going to assume that the tree is at a right angle. And so we're going to use our SOHCAHTOA, our right triangle ratios. Okay, so if we have an angle, we want to find the side opposite, but we have the side adjacent. So if you look, the tangent uses the opposite and the adjacent. So we're going to set up the tangent of the angle measure, so 71.5, equals the opposite side, which is T, over the adjacent side, which is 50. And then we need to solve for T. So if we multiply both sides by 50, we have 50 times the tangent of 71.5 equals T. Okay, in your calculator, a couple things you need to be careful of. In this case, the 71.5 was in terms of degrees. So in the mode of your calculator, make sure that your mode is set to degrees, not radians. And then to solve for T, you're going to type 50 tangent 71.5. And we get that T is 149.434. And we go back and we see that we're measuring in terms of feet. So a pretty tall tree for that one.